time. My name is Karan. I work for the engineering teams. I lead the product team for instances, hardware, big compute, HPC, a bunch of other stuff. So today I'm going to be going through like a couple of slides of some of the updates that we're going to share over the next few weeks. And obviously feel free to ask questions. So just a quick set of platform updates. So, we obviously, Leo talked about kind of the core bare metal and virtual machine infrastructure that we have today. We've been building that up over the last couple of years where, last year we had bare metal instances, we had VMs, we got a GPU instance. And so now what we're doing is kind of solidifying that infrastructure with a bunch of high-level capabilities. We are filling the gap, obviously. There's a lot of capabilities here that other cloud providers already have, and that's cool. But we're slowly but surely starting to get there. So some of the updates that we have on the compute platform, autoscale, easy concept. Customers that want to come in and be able to burst their instances using metrics like CPU utilization or anything else for that matter, maybe storage. Instance pools is an interesting one, which is basically it's a grouping construct. So it essentially allows you to templatize your instances. So if you have bare metal or VM, doesn't matter. You can say, I want to use this image, I want to use this particular SSH key, or I want to use whatever tagging that I want to put onto this instance, and then I'm going to be able to deploy it in a set of, a batch amount of clusters. So that's instance pools, and that's spread across our portfolio of instances and whatever VM, bare metal, or virtual machines. By the way, when I say shape, we really just mean size, instance shape. It's our naming convention. Fault domains. So when we launched Bare Metal Cloud, or now what it's called OCI, a couple of years ago, we introduced the fact that we have 3 availability domains within a single region. So Virginia, as an example, has 3 availability domains, 81, 82, 83. So now we're going even further down, and we're saying within a single AD, you're going to be able to get fault domains. These are independent, high availability sections within a data center. So you're going to be able to spread instances amongst these fault domains. Again, doesn't matter bare metal or virtual machines. We're going to be able to place you there. And then these types of, and then fault domains will actually flow through other capabilities as well. So for example, if you wanted to deploy a set of instances across fault domains, you could do that through instance pools. Paravirtualization. So one of the things that we talked about, from a bare metal standpoint is, we picked it for performance, but what we ended up also getting is flexibility. So if you have a 10-year-old OS, great, fantastic, bring it over. We're going to be able to run it. We're launching PV mode for custom images. Partner image catalog, fairly easy concept. So we have an ability today where you can actually deploy custom images and then provide somebody a SaaS URL to say, hey, go and you can use this image as well. Now we're just making it official. We're going to have a repository where customers, partners can actually share these images, sort of like a store. This will kind of move into a broader concept of marketplace down the line, but essentially this is the first step to that. Reboot migration. Again, fairly easy. We used to have migration already, but now we're going to have customer triggered migration. So customers are going to be able to schedule their reboots if we have security patches or other things to be able to apply to. So this is kind of like the high level of all the updates. Is quite a few more that are very small, but these are kind of the new updates from a compute standpoint. One of the other platform updates that we have that is fairly major for us is we're calling it clustered networking. So essentially, one of the things Leo talked about was the fact that, HPC customers or Exadata customers or big data customers, people that are building bespoke, very specialized clusters on premise aren't able to move to the cloud today. There's a couple of reasons for that. Bare metal is one, a couple of other reasons like storage and things. But one of the other reasons is networking, so low latency requirements. So if you want to do things like RDMA, you don't really have an option today. There's another cloud provider that does something with InfiniBand, but it doesn't scale. It's really expensive. It's not really viable in the cloud. And so we took a stab at that and we said, look, how could we do it better? And so that's what we've come up with is clustered networking. Essentially, it's built on the same kind of concepts that our front-end network substrate is built on. Essentially, what you end up getting is a 100 gig Ethernet-based super low latency RDMA network. It's a completely private network, which is isolated from the front end VCN or a virtual cloud network that we have today. So you could have a cluster of instances, and they could all be talking to each other over a private RDMA network. So you could run, HPC applications. You could run AI ML workloads as an example. So if you're running TensorFlow or distributed TensorFlow as an example, you could scale out number of GPUs with an RDMA network in the back end. We decided to use RoCE v2 for that. So we're partnering up with Mellanox and Intel on this technology. RoCE v2 really hasn't been deployed in a data center at this kind of a scale, and we really believe we've got it. We've kicked it. So we're super excited because some of the numbers that I'm going to show you is something that we've been hitting consistently because performance is really, really important in this space. And so from an HPC standpoint, we're hitting kind of 64 bytes as an example for a message size. We're hitting like 1.5 microsecond latency between nodes, just running a ping pong test as an example. We're going to support. You
said totally private, so this as in these are dedicated ports for this customer.
Correct. So basically the way we sort of design it at a data center level is essentially we have a second backend RDMA switch, and it's a multi-tiered design where we're able to connect large chunks of types of racks and instances all together. And it's completely separated from our front end. So to be able to actually get onto this network, you need to be able to SSH into a bastion host, or you need to be able to have access to your own account, aka our version of tenancy, and be able to SSH in, and then you can talk over the RDMA or the second NIC. So essentially what you're getting is a second NIC, and you're going to be able to talk over that NIC.
And again, private.
Completely private.
It's not
dedicated to you.
VRF constant.
Right. It's completely dedicated to you. It's again non-oversubscribed because obviously, if you. So the great thing is, it can be used. The primary reason for this is RDMA, of course, but you can absolutely use this for other use cases. So you can imagine a world where, actually, let me move one up. You can imagine a world where you have an Exadata and you have a bunch of GPU nodes and you have your databases on Exadata and you have lots and lots of data. Customers come to us and say, hey, I want to be able to extract more information out of my data. Can I run some AI models on it? Can I take that data? Can I run some neural nets on it and then be able to extract information? Before we're like, yeah, cool, put it on object and then turn it around and then download it onto your node and then do this and it's like, no, it's not worth it. Now what you can do is you can have your Exadata running, you can have your GPUs running, you can have block storage. It all talks to each other under the covers from a backend private network. So you can create a cluster. We call it, now we have a concept called a cluster network. You would create a cluster network and you'd put instances into it. And then those instances can talk to each other over this private network. You can still get your data in through the front end, so you could still connect it to some API, or you could still connect it to object storage. You can still connect these instances with block storage. So you can do all sorts of stuff. You could even create a high-performance storage cluster like a Lustre or a Gluster file system within this. So it's very flexible, but the intent of this is to be a very high-performance, low-latency network. With scales today, it scales up to 1,080 cores of a type of instance. We will be expanding that, over time to thousands and thousands of cores. So this is a pretty major, endeavor that we've taken the last 12 months to make it stable, scalable, and performant.
What's the pricing model?
Getting to that. Yep, getting to that. So. With that, so that is sort of the base layer technology, and then it'll make its way into our compute instances, essentially, right? So you have to have an instance that is essentially cluster network enabled to be able to use it against other things.
Card.
Exactly. So the three major instances that we are announcing are AMD-based EPYC instances. So these are instances with EPYC processors in them. We have HPC instances, which will be the first iteration of the clustered network that I spoke about just now. So essentially, you'll be able to launch a set of HPC nodes, and they can all talk to each other with clustered networking. You can have multiple clusters. You can have clusters within clusters. You it's very flexible, and you can dictate the boundaries of the actual network. And then obviously GPU instances, I feel like everybody's getting on that bandwagon, right? And they're a very important part of the ecosystem, especially from an AI ML perspective. From our perspective, it's not just AI ML, it's GPU, so it's general purpose workloads. We have lots and lots of enterprise customers. So we talked about Yellow Dog a little bit earlier. In fact, they use GPU instances for rendering. They use a program called Octane or Redshift, which is a GPU-based rendering renderer. So talked about HPC instances. These are the first iteration of what a clustered network-enabled instance looks like. So this is going to have essentially high-frequency processors from Intel. They're still Skylake generation-based today. We are going to be moving to, obviously, future generations in the future. So this is 3.7 all turbo, base frequency of 3.0. Local NVMe storage. So if you're running lots of MPI applications in the HPC industry, so Intel MPI, IBM Platform MPI, Open MPI, MS MPI, they're all supported. They all require lots of checkpointing during the jobs when you're running a big job. And so that's why we've got local NVMe storage. And the same performance SLAs apply to that as well. Front-end network, 25 gig, and then a private 100 gig backend network. Obviously, if you deploy 2 of them, they'll talk over a private backend network. You can obviously deploy a single one to do just CPU-based compute as well. 7.5 cents per core per hour is going to be our cost. Pay-as-you-go, on demand per hour. You get everything included that you see on that. So a comparable instance, as an example, is something like a C5, Amazon C5. I think they call it compute-intensive instances from AWS. If you look at their pay-as-you-go price, I think it's like way more than that anyway. So, and there's no RDMA, all that jazz. So, we're going to be releasing the actual instance in general availability, and we're going to be public previewing the cluster networking capabilities. So if you have MPI workloads or RDMA workloads, you're going to be able to do that. Some numbers that we've been running. So this is an application called Ansys Fluent. Who knows who Ansys is, maybe? Yeah? EDA, yeah. So chip design. If you drive a car, most likely that car was built using Ansys products. Ansys builds a lot of computational fluid dynamics, things like crash testing, FDA testing, material testing, glass, plastics, materials, that sort of thing. And so the thing that matters to an engineer is how quickly can I run my simulation and how far up can I scale my job. Generally, from an RDMA perspective, most jobs fail or start to go downtrend at about like 512 cores, maybe 256, depending on the code. We're seeing really, really good scale. In fact, we're scaling linearly beyond 512 cores for a single job, which is kind of, it's basically better than on-prem today in that sense. Again, this is running Linpack, fairly common benchmark, similar results. By the way, this is all comparing that instance type that we have against a C5 and a C5D. And then we have a couple of numbers. So we understand that, in isolation, looking at an instance versus an instance is kind of wrong in some sense. What we're really competing against is on-premise deployments of these types of things. And that's what we're also now comparing against on-premise clusters as well. So in fact, the blue line or the blue bar is comparing against an on-premise deployment of such. So from a node-to-node perspective, we're pretty much roundabout there in terms of performance. So this is again Linpack as well. Memory bandwidth, very important for HPC applications. Again, so we're kind of running through a slew of benchmarks there. So this is running Stream, SpecInt, SpecCrate, and this is again running against on-premise clusters as well. So the idea here is, we can never be better than on-premise. The idea is to be just as good. We'll try to be better, but on-premise is like essentially the benchmark, right? And that's what we're trying to get to. And again, this is all pay-as-you-go, on-demand, multiple regions. You can deploy the HPC instances in US and Europe. We're going to be expanding to Asia as well very soon. The next set of instances, next set of updates, AMD Epoch. Essentially, it's going to be up to 64 cores of Epoch, and they're going to be the highest memory bandwidth. Essentially, from our perspective, these are going to open some new markets for us. We talked about the fact that our base customer base is enterprise customers, but this is really going to open up some of the more cost-sensitive workloads that we see out there, like containers and things like that. So customers, that want to run dev test workloads or CI/CD and things like that. So that's why it's priced appropriately at 3 cents a core hour. That's the pay-as-you-go cost. Last I checked a couple of hours ago, it's like literally the cheapest instance type you could buy, barring burstable instances as an example from AWS. So as a pay-as-you-go, get a VM. It's going to be the cheapest thing out there, period. It also runs Oracle databases. It runs Oracle applications, and those are all certified, tested. They perform really well. So that's an obvious one. Again, we're going to have bare metal, and we're going to have VM as well. So one of the nice things about having bare metal is the fact that if you have an existing deployment of a virtualized stack, you can literally lift and shift on top of our bare metal node. Now that we have paravirtualization, you can do that even better with old OSs. And then obviously we have VMs if you want to use VMs as well directly. This is again showing memory bandwidth, which is kind of one of the nice things about AMD Epoch is better memory bandwidth, and so we get that obviously with that chipset. And then, in fact, a couple of weeks ago, we announced in Munich, Germany, at the keynote, Jensen on stage announced that Oracle Cloud is going to be the first to market with an HGX2 in the cloud on demand per hour. So this is going to be 8 to 16. We're still at 8 right now, but 8 to 16 GPUs of 32 gig Volta V100s. They're all going to be interconnected with NVSwitch, which is NVIDIA's new silicon that allows all GPUs to talk to all other GPUs without losing an ounce of, or without doing an extra hop, essentially. So today we have an HGX1 in the cloud already today, available across the globe in our regions. We've adopted now the HGX2 design for our next generation of instances. Obviously, the design is OCP design. It's open from NVIDIA. It's multiple vendors coming to build that. We're using that chassis design, but for our head node, we're picking obviously a couple of different specs. So we've got a high frequency processor there. We've got lots of RAM if you want to do graph processing and things like that. And then this is also going to be clustered network enabled. So if you want your you can imagine a world where you want to run some simulation, but then you want to take that data and put it into a GPU instance. And so, or you want to do some, database processing, and then you want to move that data into GPU and vice versa. So we're trying to open up some new types of use cases and scenarios that just weren't possible before.
How big is the HPC market? Do you see it?
Billions and billions of dollars. I mean, it's kind of like that's a standard answer, but what we're really targeting is product development. Right, so these are like big manufacturing companies, big automotive companies, big medical healthcare companies, robotics, oil and gas. These are people doing reservoir simulation. These are people doing crash testing. People used to test, aerodynamics on a car in an actual tunnel and run wind through it. Right now, they actually do 10,000 simulations. That stuff is really computationally intensive, and so we think that's a huge market. Most of it's all still on-premise. They're buying, our competitors there in that case aren't other cloud providers. It's actually the OEMs, right, that are actually selling this stuff to those customers. And then, to sort of kind of cement the fact that we're really going after this market, we picked a vendor that we've been working with for a little while. and so this announcement's going to come out pretty soon. So we're partnering up with Altair to provide an engineering simulation service on Oracle Cloud. So essentially, this is going to use some of the technology I talked about in terms of clustered networking, RDMA, GPUs, the whole 9 yards. And this is really putting, the power of sort of like a supercomputer in front of an engineer's fingertips. So this literally means an engineer working for an automotive company can go into their application on Altair and literally click a button, and it just goes and magically does stuff in Oracle Cloud. They don't need to know about the cloud. It's all obfuscated, completely managed by Altair, completely built on Oracle Cloud. And so this is really, really exciting for us because it's kind of never been done before, in the sense like no one really offers these kind of products. They're all still on perpetual license servers. You got to go and run a Flexera license server, and then these things cost like $100,000 a seat, for a license. And there's big companies that have large deals with other IC vendors. So this is kind of a new uncharted territory that we want to try and open. So this is going to be using FluidX and NanoX, which is their GPU-based computational fluid dynamics code. It's going to be running natively on Oracle Cloud. They're going to be managing it, and of course, the cost is going to be obviously relative to what we have here. So.
Altair is a company I founded in 1985 with a vision to use simulation to drive design and decision-making. Through the years, it's evolved from validation studies replacing test to moving simulation up front to almost synthesized designs. Now that we move to the cloud, the opportunity to really do unlimited size studies just open the possibilities up.
GPUs compared to CPUs have a massive compute power, and if you develop software which is designed to be executed on GPUs, you get a massive speed up. Altair is developing software which is designed to be executed on GPU hardware. As an example, we have Altair Ultra FluidX, our solution for external aerodynamics. A fully detailed car can be run in a transient mode overnight. And this also opens up the door to talk to the design studios and bring the virtual wind tunnel to the designer's desk. External aerodynamics produces gigabytes of results, and you don't want to transfer these results to your local machine. One big advantage of the cloud is that you can leave the big data on the cloud itself. This means your laptop can be pretty light, but the massive data stays in the cloud. You can sit in the plane or in a subway and still monitor your run, and you can even display your results because we just transfer a very thin slice through your flow domain to your local tablet, for example.
Challenges that customers face are time to market and to increase the speed of innovation. We are launching an on-demand computational fluid dynamics virtual appliance on the public cloud with our Ultra FluidX and Nano FluidX applications leveraging the high-end GPUs on the Oracle Cloud infrastructure. We have leveraged the Oracle Cloud infrastructure because Oracle is the first cloud provider to provide bare metal computing resources to match on-premises performance. They have a flat, low latency, high-speed network for highly parallelized jobs, world-class NVMe-based storage both for local scratch and block, and global access to the resources across all regions with high confidence in security and compliance. We were looking for the best price performance, and we found that with Oracle Cloud infrastructure.
Some of the work that we've been doing with a lot of different providers. This one's actually SI called TotalCAE. They're based in the US in Detroit. They do a lot of work for managing clusters for some of the biggest automotive companies in US. You know the names, and so they've been doing a lot of work with us for that. So this was done on our cluster network. This was a simulation that was done, and in fact, I may have a minute just to quickly show you. The 3D model that this was done at, so we know it's not fake in that sense. So this is a GPU instance that is running in our Virginia data center. And this is running ParaView, which is an application, visualization application. And what I'm really showing you here is it's a Wi-Fi connection. I'm actually on the public Wi-Fi or guest Wi-Fi. And this is sitting in a Virginia data center. And the idea here is that you're going to be able to go design these things in real time, be able to change things, like you could change the material of the car, go run a simulation on the clustered network, feed those results back into a GPU and be able to redesign it again. You could be sitting in a coffee shop, you could be doing whatever you want. This stuff used to take like 16, 20 hours to run. You could do it pretty much dynamically now. You can run a simulation in 10 minutes and come back and do that. So this is ParaView running on a GPU instance. Another one quickly to show you is this is another GPU instance. This is I think sitting in actually Frankfurt, and this is running Ansys Discovery Live, which is a commercial application to do similar type of stuff, and this is doing essentially air simulation analysis on a truck. So again, the idea is a full end-to-end workload in the cloud, as opposed to like, hey, bring your application, rip it up into pieces, and then go and use some fancy API. No, you can bring your existing workload. It runs better, if not, the same, and then it's going to be just as cost efficient to run it on Oracle Cloud. So that's kind of a quick dive into some of the updates. Any questions?
Quick question, actually, which is sort of out of scope of the new stuff you're showing off here, but performance is obviously a very key priority for you guys.
Yes.
How have you found the issues around mitigations for Heartbleed and Spectre? Has that been a problem, an issue, an impact on?
I personally haven't seen that much.
Okay.
I know engineers back at Oracle Cloud have been working around the clock every time one of these things comes out, and I know there's a standard answer that we have to give out. So, but from my perspectives, talking to customers, I haven't seen that much.
Okay.
It's partly one of the reasons why we're also introducing some additional vendors into the play as well, right? Like, so customers have choice. It doesn't matter. One or the other, you can actually go to the other one as well. So AMD, as an example, is not susceptible to Spectre.
Not the same type of ones, yeah.
Not the same type of bugs, yeah.
Okay.
And with the new generation of compute, the GPU intensive compute, you facing that launch across the regions, or are they happening all simultaneously?
They're going to be simultaneous. Right now, we're targeting Q1 of next year. So right now, we're working with NVIDIA on their sort of different topology of instances. And so, yeah, it's going to be across US, Europe, and also APAC when we have those regions live. Yeah, so generally what you'll find is like that we will have our major regions like Virginia, Frankfurt, Phoenix, London, where literally, like if we're talking about a worldwide, yeah, they'll be worldwide, but they'll be like in the instance of like a couple of days here, a couple of days there. But in all essence, yes, generally available across all our data centers.